topics in physics and as well as every other subject.
This call is now being recorded.
I think our last class we began something on
This call is now taking notes.
we did heat measurement. That was the topic we did the last time. Heat measurement, that measurement of heat. And the persons that attended the class, I believe they've mastered how to navigate problems involving heat measurement. We saw how we can use the formula for that's the relationship between the heat quantity and the specific heat capacity. We also saw that of latent heat, and we talked about two types of latent heat. We said we have latent heat of fusion and vaporization. So the videos are all there for all the classes you've made so far. So if you feel there's a need, you can always go and check out those videos and then take notes of the things we've done so far. But today, we'll be looking at photoelectric effects. Photoelectric effects. Have you heard of photoelectric effects, both of you? Let me start with you. Okay, you've not. What about you, Christine?
No,
okay. Okay. All right. Now, look at this diagram. What can you really tell about the diagram? I took the diagram actually I just saw it online. I picked it out because it explains what I want to do for the class. So what can you really say about this diagram? What do you think is happening? That's the question. What do you think is really happening?
I think that the force conducting the molecules are lesser. They don't have enough forces.
Force. There's no force on this matter right now. You're bringing in a total new concept. Okay, but that's a good trial. Christine, what do you think is happening?
The light is being mirrored onto the surface.
Okay, and as a result?
The electrons are being removed.
Thank you. Now, that's exactly what I want you to observe from this diagram. Now, clearly, you can see that the label, you can see where it's been labeled incident lights. So that is the light, this one. The light, just like the sun, this is a metal surface. The metal surface, think about the metal surface to be any kind of metal surface. In fact, a good kind of illustration is your solar panel or even your roof. Now you see, light hits the metal surface and electrons, which are already domiciled on this metal surface, is being ejected or removed, just like you said. It's been ejected. That is what photoelectric effect is all about. That is all. So this diagram illustrates, in fact, this is a summary of the entire topic. Light struck a metal surface, and as a result, we have what we call ejection of electron. There are two things that can happen when that can happen to a metal surface. One is as a result of light, another is as a result of heat. If being struck incident on a metal surface, we have what we call thermionic emission. All right, so thermionic emission is different from photoelectric effect because in thermionic emission is also electrons being ejected as a function of heat being incident on that metal surface. But in photoelectric effect, we are considering the light. All right, so sunlight, not necessarily the heat. So the light struck on the metal surface, and then you see electrons are being ejected, and that is what photoelectric effect is all about. Now, the photoelectric effect I put down here was discovered by, this is just a little background. It doesn't necessarily imply that you will be asked, just for you to have a good idea. And just in case you might still be asking your OBJs or stuff like that, you can come across questions like who founded photoelectric effect and then what year, stuff like that. All right. So, but the idea why you have this thing here, just for you to have a general overview, a broad overview of what the whole concept is all about. So I put down that photoelectric effect was discovered by Heinrich Hertz in 1887. So he was the one that discovered photoelectric effect. So take note of the person's name. The person that discovered it is called Henry Keynes. So this is the name here. Henry Keynes was the founder or the person that discovered photoelectric effect in the year 1887. And now, how then do we define, please, if you know your background will be noisy, you may just do well to turn off your mic, okay? You can turn it on if you want to ask a question or any contribution. All right. So now, look at the definition here. I said the photoelectric effect is a phenomenon in which electrons are emitted from the surface of a substance when certain electromagnetic radiations falls on it. Now, this substance here, please have in mind that the substance in question are metals, okay? So when electrons are being emitted from the surface of a metal due to what? Electromagnetic radiation. There are a few things to pick out here. Number one is that electrons are being emitted. So anytime you talk about photoelectric effect, there is usually an emission of what? Electron. And this emission of electron is due to electromagnetic what? Radiation. Is it electromagnetic radiation? Electromagnetic radiation can be the light coming from your sun, all right? So anytime the light coming from your sun strikes a metal surface, electrons are being emitted. That emission of electron is what we call photoelectric effect. So that is what it is, and this is what this diagram here is actually talking about. The diagram is just gives us a clear picture of what happens when light incident on a metal surface, and then you can see clearly there is an ejection of electrons. All right. So the next thing I want us to talk about is the work function. Having understood the concept of photoelectric effect, we need to understand what is work function. Now, basically, if I ask you to define work, who can help me? Who can define work? Primarily, your elementary physics. What is work? Or when do we say work is done in physics? Someone should come to the rescue. Christine, you were the first to join the class, so I may still call you. When do we say work is done in physics?
When energy is transferred.
When energy is transferred, okay? All right, any other contribution? Does it mean, so what you're implying is that anytime energy is being transferred, work is done? Is that what you're trying to say?
Yes, sir.
Okay, now imagine that I am pushing, let's say I'm pushing a wall. Let's say you walked into a room, then you see me trying to push a wall, or right where you are, you see maybe a sibling or someone just walked into the room and the person is trying to push a wall, and the person pushes the wall for like 10 minutes. Now, will you say, won't that person lose energy?
No, sir.
The person will. Maybe you have to try it out. So what I want you to do after this class, just start pushing the wall in your room. Just push it, be pushing it, and push it for like 10 minutes. You find out that over time, you just get tired. Do you understand that? Because you are doing, so energy is being lost, but you're not doing any work. Do you understand that? Energy is being lost because it takes energy to push anything, but work is not being done. So who can explain from my little lights that I've just shown now, who can tell us what exactly, or when do we say work is done in physics? Now, please, can you please mute yourself?
Sorry, I want to let me leave that room. Let me work the energy transfer that occurs when an object is moved over a distance by an external force.
No, you are saying so many things. Just I didn't hear you. So come again.
And okay, it's the energy transfer that occurs when an object is moved by an external force.
Okay. I love the fact that you mentioned moved. That is the only thing I'm looking for. The fact that you said moved. All right. Let's forget about every other thing you said. Now, the idea basically, anytime we say work is done, have it in mind that an object has moved a distance. All right. That's the concept. So work is not done until distance is being covered. For example, you move from where you are, let's say You walk from point A to point B. So you say work is done because you've been able to move from one point to another. But a boy pushing a wall and pushes the wall for like 10 minutes, we wouldn't say work is done because after 10 minutes, that wall wouldn't have moved an inch. So work is not being done. So work is done anytime a force moves an object through a distance. All right. Now, in the concept of this photoelectric effect, now you notice that the electrons are being ejected. Of course, they moved. Is that not true? So they sustain motion. They were initially at the metal surface, but the moment the sun strikes on that metal surface, the electrons are being ejected. So we can say that work is done. Do you understand that? So that minimum amount of work that is needed to remove an electron from its energy level to overcome the forces binding its surface is what we call work function. Do you understand what I'm saying?
Yes, sir.
Okay. So that is what this little slide is talking about. The minimum amount of work that is needed to remove those electrons or to remove an electron from its energy level to overcome forces binding those surfaces is what we call work function. All right? Work function. That is what work function is. So anytime you hear work function in physics or in this topic, just consider the energy that makes those electrons to be ejected, the energy that pulls those electrons, that makes them to move from the surface that makes them ejected from the metal surface. That is what is called work function. So you can see I put down here that this is known as work function. And of course, work function can be, the units can be in electron volts. Unit can be in electron volts. Many a time, in fact, anytime you hear work, of course, the standard unit for work, who can help me with the standard unit for work? What's the standard unit for work generally? No one is saying anything now. Look at. All right. The standard unit for work is actually joules. Work is measured in joules. So when you hear 1 joule, the same energy, the same unit for energy. Of course, energy is what proportional to what work done. So work done is measured in joules as well as energy measured in joules. So that minimum amount of energy that is required to pull the electron from that metal surface called work function. And this work function can be given in electron volts. Sometimes it wouldn't be given in joules, all right? So it can be given in electron volts. Now the question is, what exactly is electron volt? And what's the relationship between an electron volt, 1 electron volt, and joules? What's the relationship? Now, firstly, you can see clearly on the slide that 1 electron volt is the work done. 1 electron volt is the work done when when 1 electron is transferred between 1 point with a potential difference of 1 volt. That is what an electron volt is. So if you ask to define electron volt, you tell them that 1 electron volt is simply that work done when an electron is transferred between 2 points with a potential difference of 1 volt. So the work that is being done anytime we have a transfer of electron between 2 points, from point A to point B, that is called electron volt. And that electron volt can be converted to joules. All right. So 1 electron volt is more like having, we will say 1 electron volt is actually the charge of an electron. Of course, the charge of an electron is 1.62602 times 10 raised to power minus 19. This is the charge of an electron. Of course, you know, charge is measured in coulombs, all right? So this is the charge of an electron multiplied by 1 volt, all right, which is the potential difference, multiplied by 1 volt. So if I multiply this charge in coulombs and then multiply the potential difference in volts, the product of these two things is going to give me our conversion in joules. So everything here, 1 electron volt would be, of course, anything multiplied by 1 gives us back that same thing. All right. So it means that if I want to convert 1 electron volt to joules, it simply becomes 1.602 times 10 to the minus 19 joules, because multiplying this charge by 1 doesn't really change what the magnitude will be. The only thing is that, of course, charge is in coulombs, and then the potential difference V is what? In volts. And anytime you multiply coulombs and volt, the outcome is what? Joules. So this is how to convert 1 electron volt to what? Joules. So what that means is that if you are trying to solve a problem where you need to convert from electron volt to joule, simply multiply the value given to you in electron volt by 1.602 times 10 raised to the power minus 19. This minus 19 here. Sometimes it might be given to you, they'll just give you 1.6, all right? They'll just approximate 1.602 to 1.6. But have it in mind that for you to convert from electron volt to joules, simply multiply that magnitude, that value given to you by 1.602 times 10 to the minus 19. That gives you its value in joules. Now we've talked about photoelectric effect. We've talked about who discovered photoelectric effects. We've talked about the year in which it was discovered, and we've talked about the work function. And we've also discussed the electron volts. Okay. So this was where I did the little calculation, just like I showed you now. So 1 electron volt, I've done the whole of that. Okay. Now the next thing I want to talk about is the threshold frequency. Threshold frequency. Now, what is threshold frequency? Now, there's something I forgot to say when I started this explanation, when I defined photoelectric effects. Now, remember we said, who can remind me what I said about photoelectric effect? What is photoelectric effect? Someone should tell me what I said. No. If no one responds, then it means people don't want us to continue. I need to call all of you by names. Amaka Eze, help us.
Sir,
What is photoelectric effects?
can I define in my own understanding?
Yes, your own understanding. It doesn't need to be verbatim, but in line with what I just said.
Okay. For the electric effects is defined as a process whereby a light is being directed to a metal material, which causes an ejection and a removal of the electrons out of the metals on the effect of
Okay,
the light inclined.
okay. That's a good one. Now, someone else. Who else? Melody, can you come to the rescue? What is photoelectric effect? Christine, you were here, you were with me when I started the class. What is photoelectric effect?
The photoelectric effect is when the light is subjected to the metal surface and the electrons are admitted into the surrounding.
Okay. Now, in a nutshell, you both have spoken well, but in a nutshell, photoelectric effect is just the emission of electron anytime light incident on a metal surface. All right, that is what photoelectric effect is all about. So don't try to think about it as something big. And it is the emission of electron when light incidents the metal surface. And that is what photoelectric effect is all about. Now, before the electron is being emitted, before those electrons is being ejected or being removed from the surface of from the surface of the metal, there is usually a minimum frequency, a minimum required frequency that is required for those electrons to be ejected. So what I'm trying to say is that if the light that is being struck, that is being incident on that metal surface doesn't beat this frequency, then there will be no ejection of what? Electron. And that frequency is known as threshold frequency. So below threshold frequency, no emission occurs, no ejection of electron occurs. Do you understand that? So that is why we say that threshold frequency, as you can see, is the minimum frequency of the radiation that will cause a photoelectric effect on a certain surface. What that means is that if the light that is being incident on the metal surface doesn't have a frequency that is equal or greater than the threshold frequency, there will be no emission. There will be no emission of electron. So intensity might be there, but if the frequency is not up to that threshold frequency, then there will be no emission of those electrons. And that is what threshold frequency is all about. And usually, threshold frequency has a symbol F naught. So by the time I give you the equation and you see F naught talks about the threshold frequency. Again, it is a minimum frequency. Take note, we said minimum. Minimum means that below this frequency, no emission occurs. There is no photoelectric effect. Below it, there is no emission or ejection of electron. So it is a minimum frequency that is required for photoelectric effect to take place, to occur. That is it. Okay. So also, of course, you can see there's a commentary added there. The higher the work function, the higher the threshold frequency, and also vice versa. So if the work function, it means that the threshold frequency depends directly on the work function. This threshold frequency, the equation for the work function, I don't know whether I gave that. I will still do that along the line, even as we proceed with this class. I should have given you an equation for the work function. Let me go back a little. Okay, I didn't give any equation. But this work function has a formula. Now see, look at the formula here. I just went back to the work function because of that statement I made, I added there. Now, the work function W, take note that the work function W varies directly as the threshold frequency F naught. What it means is that if the work function increases, the threshold frequency also increases. All right. So from here, of course, you know in mathematics, anytime you remove the symbol of proportionality, you must bring in a constant. And in this case, I can write that my work function W is equal to H F naught, where this H is a constant of proportionality known as Planck's constant. All right. So you see that the threshold frequency is directly dependent on the work function. So if the work function increases, the threshold frequency also increases. If the work function is going down, it means if the threshold frequency is minimum, it means that the work function is also small. All right. Remember, we say the work function, how we define it, the minimum energy that is required to cause ejection to occur. All right. So that is that for that. So take note of this equation that W, some textbook, or you can see some book, they wouldn't use W, they will use symbol like psi. So this is psi, that psi is equal to HF naught. So the symbol is not really what matters. What matters is you having in mind that the work function, whatever thing you're using to represent it, is equal to HF naught. Where this H is Planck's constant, and I'll tell you what Planck's constant is as we progress with the class. So the reason for that is just to explain that this last statement, that the higher the work function, also the higher the threshold frequency. And I've shown you that by equation. If the work function is increasing, the threshold frequency also does increases. Now, we have factors affecting the photoelectric effect. The factors affecting the photoelectric effect, from what we've said so far, of course, you know that the work function affects the photoelectric effect. Another thing is also the intensity of the incident radiation. When we talk about intensity, of course, you know what intensity, when we say intensity, how the energy with which the light is coming with, all right? So the intensity also affects the photoelectric effect, as you can see clearly, and also the work function also do affect the photoelectric effect. So we say the rate of emission of photoelectrons is directly proportional to the intensity of the incident radiation. So the energy with which the light is coming with also affects the amount of electrons that will be ejected from that metal surface. All right. So you can do well to read up and go back to the videos, understand, master the fact that the work function, the photoelectric effect depends on the intensity of the incident radiation, and also it depends on the work function of the metal surface. So I showed us Planck's constant from when I wrote the equation that W equals HF naught. Now, how then do we define the Planck's constant? That is the next thing I want us to look at. I'm trying to be a little bit fast because I believe this is a recorded class, so everyone can always go back to the video and see things. You can pause as many times as you want, take it backward as many times as you want to ensure you grab it better and better. All right. But I'm just trying to be fast, so we wouldn't spend time doing less. But at any point you feel you have a question, you can always ask, so that let it not be that you are not following at all. Okay. So the next thing we'll look at is the Planck's constant. Planck's constant. Planck's constant. So what is the Planck's constant? Of course, from what I gave you, that W, record this equation, that W equals HF naught. What happened to my pen? Okay. W equals HF naught. And I said that this H here is a Planck's constant and it has a value. What is the value of the Planck's constant? The value is 6.63 times 10 raised to the power minus 24 joules second. So anytime you see Planck's constants, the symbol is H, small letter H. Once you see this Planck's constant in a question, or you're solving a problem that involves using Planck's constant, have it in mind that the value of that H is given as 6.63 times 10 to the minus 34 joule second. And that is it. And of course, it was a Max Planck that predicted the energy of an oscillating atom. And we'll see the whole of that, what he meant. We'll see how that we can combine the Einstein's energy equation, combine the Max Planck's energy equation, and then we can now together we form what we call the photoelectric equation. And that is what we use in solving problems involving photoelectric effect. So when we get to that, I will explain more on that equation there. Okay. Now take note of this. Take note of this, that according to Einstein's equation, that the energy, it is the energy of the photon. The energy of a photon is given as E equals HF. The energy of the incident photon, when we talk about photon is talking about light rays, all right? The ray of light, just the ray of light is what we refer to as photon. So the energy of the photon, according to Einstein, is given by this equation, E equals HF. All right. So, but you know, from your element, from what you did, I think, if you've ever done something on wave, which I believe most of you should have encountered problems on wave, you know the popular equation, popular wave equation, that V is equals to what? F lambda. And of course, when we start discussing electromagnetic waves, this V can be written as what? C, where C is the speed of the light, all right? So speed, C, equals F multiplied by the wavelength, lambda. And if I make frequency subject here, if I try to make frequency the subject of this equation, I'll be having that frequency F equals C all over lambda. And that is how we got the equation here. This is the Einstein's photoelectric equation. Meanwhile, this is how we calculate the energy of the photon. This is not the broad overview of the whole photoelectric equation. We use this equation to calculate the energy of the incident photon. All right. So the energy of the incident photon can be calculated by this Einstein's photoelectric equation, where we have that E is equal to HF or E equals HC all over lambda. There are times you can use HF, you can combine the HF equals HC over lambda to solve a given problem. So have it in mind that E equals HF or E equals HC all over lambda, where the F there is the frequency of the photon, all right? And then the C is the speed of light, and then the lambda is the wavelength of that of the wave. I want to write some few things here. Now, generally, the photoelectric equation, the photoelectric equation is given as E equals HF naught. No, let me write it out plainly. It's given by E equals W, which is a work function multiplying by the kinetic energy. The kinetic energy, which is the energy with which the electrons are being ejected. Of course, you know, anytime something sustains a motion, the energy responsible for motion is called kinetic energy. All right. So this is the general equation for photoelectric effect. So we combine the Einstein's photoelectric energy equation, we combine the whole thing together with the work function. This E here, remember, we said that the Einstein's photoelectric equation is given by what? HF. But this HF also, which is the energy of the photon, is equal to the work function W and also the kinetic energy, the sum of the work function and the kinetic energy. So the kinetic energy is the energy with which the photon moves, and the work function is the minimum energy required for emission to occur. So if you sum up the work function, which is the minimum energy, and the kinetic energy, it's also equal to the what? Energy of that photon. All right. But we've already established the fact that E is equals to HF. We already know that E equals HF. And also we know that W is equals to what? HF naught, where F naught is the threshold frequency. And of course, you know that kinetic energy is given as 1 all over 2 mv squared. This one is basic. All right. So if I try to put every of this equation into one equation, it means that I can rewrite this equation here. Instead of having E equals W over KE, I can write this equation to mean that, let me do that properly. So this general equation can be further written as E, which is HF, is equals to HF naught plus 1 all over 2 mv squared. So you see that. So I can actually put in what their values are, and the equation becomes a bit longer, but it's not actually anything long. H is your Planck's constant. F is the threshold frequency. Then that's F naught, please. F naught is the threshold frequency. F is the frequency of the incident photon. All right. So take note of these things, that F is the frequency of the incident photon. F naught is the threshold frequency. Remember, we said the threshold frequency is the frequency below which no emission occur. So if the frequency of the incident photon doesn't exceed or doesn't equal the threshold frequency, there will be no emission. All right. And the product of that threshold frequency alongside the Planck's constant gives us the work function. So where the M there is the mass of the electron. Of course, V talks about the speed of that with which the electron is being ejected. So have this in mind, that this is this meaning of all these symbols, so that anytime you see it in equation, you know what they imply. And that was why I wrote this here. Look at this equation. What I did is just to tell you why I put down this equation here. That's HF is equals to what? W plus 1 over 2 mv squared. The only thing is that I didn't substitute W into the equation, but I already told you that W is what? HF naught. So if I put HF naught into this equation, I'll be getting exactly what I have here. That's what? HF equals HF naught plus 1 over 2 mv squared. And this is the general equation for solving problems involving photoelectric effects. So take note of that, just in case you're being asked to do anything. Okay, now let's try to see how we can engage the formula in solving a problem. Let's try to see how we can engage that formula in solving a problem. But before we even solve a problem, I would want someone to ask a question just in case you are confused at any point. Any question so far? If there's no question, you just react, give a thumbs up. Let me be sure you're all following so we can just proceed. Melody, you're not with us. Melody, do you have any question?
So I don't know how to say my network is bad.
Oh, yeah. So what you will do is that later, you can always go back to the video and check it over and over again. So the things you miss, you can be able to get them while you watch the video. All right, look at this question. This question says that the work function of a tungsten is 4.52 electron volt. Find the cutoff potential for photoelectrons when a tungsten surface is illuminated with radiation of wavelength 2.5. That times, no, wait. This is 2.5 meters. There is supposed to be times 10 raised to power. Oh my God, I missed something. I mixed up something good. Mix up something. I think this is 2.5 times 10 raised to power 7, please. Times 10 raised to power 7, if I'm not mistaken. But what will happen is that I will just work with the value I have here. All right. I'll just keep up with this value and work with it in solving this problem. So, but have it in mind that anything you are being given, that's what you use. But in this case, this is supposed to be 2.5 times 10 to the 7. I don't know how that was omitted while I was trying to put this together. So now they ask us to find work function, right? Now let's write out the parameters. In physics, anytime a question is being given to you, the very first thing you do before you even proceed to solve the problem is to write out your parameters. Writing out your parameters will help the problem and the job, everything becomes easier for you to do. Now they say the work function solution. The work function of a tungsten is 4.52 electron volts. 4.52 electron volt. They say we should find the cutoff potential. Cutoff potential, that's V. Let me call it V subscript C. All right, is unknown. For find the cutoff potential for photoelectrons when a tungsten is illuminated with radiation of wavelength 2.50. So I'll just add 2.50 times 10 to the 7. All right. So this is our wavelength lambda is equal to 2.50 times 10 raised to power 7 meters. And then, of course, it gave us the Planck's constant H. Planck's constant H is giving us 6.62 times 10. Oh my goodness. Raised to power minus 34 joules second. All right. So you see, even for the Planck's constant, the not the entire value was given. So have it in mind, Planck's constant is a constant, and the constant is 6.62 times 10 to the minus 34 joules second. And that's exactly what we have here. So how do we find the cutoff frequency, the cutoff potential, according to the question? How do we find the cutoff potential? Now, look at it. They say the work function of a tungsten. So they gave us one function. Remember this equation. Recall this equation that E is equal to the work function multiplying the kinetic energy, Ke. Always have this equation in your mind. And clearly, the energy wasn't given to me. The energy wasn't given to me, but the work function was given. But they gave me the wavelengths and they gave me the Planck's constant. All right. So how do I find? I was given the wavelengths and also I was given my Planck's constant. So it means I need to make my substitution here to get exactly what I'm looking for. Now the question is what exactly do I even do? Because I need to understand what I'm being asked to do. What is cutoff potential? I didn't explain that. And since I didn't explain that, I would have solved this question first before I do this one here. So it doesn't look like I'm doing something entirely different from the example I want us to do. So I would prefer, let me solve this question right here, this one. After solving this one, then I can go back and solve the one we started already. Because somebody might ask me what exactly is cutoff potential. But before we do that, let's solve this problem that involves exactly the formula I gave to you. And the question says that you calculate the frequency. So take down the question, calculate the frequency of the photon whose energy required to eject a surface electron with kinetic function of this if the work function of the metal is given as that. So please take down this problem, write it down so we can quickly solve this one before we go back to the other one. And you just have about maybe 30 seconds, 45 seconds to put the questions down. Okay, so I want to believe we've solved it, we've copied down the question. So let's proceed. Now, solution. We also write out the parameters given to us. Let me try to zoom in a little. So from the question, they say we should calculate the frequency of the photon. So we're looking for frequency of photon, so F. So we're looking for F. I'll write that F here. Unknown. Whose energy required to eject a surface electron with kinetic function of 1.97 times 10 to the 16 electron volt. So they gave us our kinetic energy, Ke, as 1.97 times 10 to the 16, 1.97 times 10, it is 10, raised to the power 16 electron volts. And then they also gave us that if the work function of the metal is 1.33 times 10 to the 16 electron volts, so if the work function W is 1.33 times 10 raised to power, minus 16 electron volts, minus 16 electron volts. And that was all they gave to us. All right. And clearly, you already know how to make conversions. I told you, anytime you have the values given to you in electron volts, you can convert them to joules. And since we are looking for frequency, the unit of frequency is hertz, and hertz is obtained everything. It means that if you have to solve for frequency, everything here has to be in standard units. All right. We have to keep up with what? Our standard unit. So we should ensure we work with standard units so we can find what the frequency is. So let's convert kinetic energy by multiplying. So I have 1.97 times 10 to the what? 16, which is in electron volts. So to change it to joules, I have to multiply this value by what? 1.602 times 10 to the power of minus 19. Let me just use 1.6. Why is my distance freezing? 1.6 times 10 raised to the power minus 19. So someone should do this and tell me what the answer is. Then also for the kinetic, for the work function, also multiply the 1.33 times 10 to the minus 16 is in electron volts. So we also have to multiply by what? 1.6 times 10 to the power minus 19. So we can change it to joules. So multiply that for the kinetic energy. What would this give us? Someone should tell me the value of this. So what's the kinetic energy in joules, please? Someone should multiply 1.97 times 10 to the 16, multiply 1.6 times 10 to the minus 19. Does it mean no one has a calculator? Lucas, multiply that value and tell me what you have. Every one of you here present should have a calculator. I don't have my own calculator right here. And that's because I believe every one of you coming for a physics class should at least have a calculator. So please go back and check what is the product, what will be the value when you multiply 1.97 times 10 to the 16 by 1.6 times 10 to the minus 19. That person, please, with the background music, can you please mute yourself? I'm patiently waiting for us to respond. If we don't respond, it means that you people don't want us to solve this thing. I want you guys to respond to it. Multiply 1.97 times 10 to the 16 by 1.6 times 10 to the minus 19. What will it give us? I can't hear you.
0.152 times 10 raised to the power minus 2.
If I heard it clearly, you said 3.152 times 10 raised to the power minus 3 joules. All right. So also change the work function. Change the work function to joules. What will it be? By multiplying 1.33 times 10 to the minus 16 by 1.6 times 10 to the minus 19. What is the product what is the value when 1.33 times 10 to the minus 16 is multiplied by 1.6 times 10 to the minus 19? You guys are taking time.
2.128 times 10 to the power of minus 35.
2.128
times 10 to the power of minus 35.
times 10 minus 35 joules. So these are the values all given in joules. All right. So let's now use them in solving our question. So the next thing we'll do, record the equation. Recall that E is what? The work function W plus the kinetic energy, KE. And clearly we were given KE, we're given the work function, but we were asked to find the frequency. How do we find frequency? But you know that E is equal to what? F lambda, sorry, HF. HF, that E is equal to HF. Where this H here is a Planck's constant, which was also given in the question, and then F is the frequency. So if I put this F into this equation, I'll be having that my E becomes, sorry, my HF, I'll have that HF is equal to the work function adding up with the word kinetic energy. And if I make F subject formula, it means that my F divide both sides by H will give me the work function plus the kinetic energy divided by H. So this is what it is. So the next thing would be to plug in the parameters. All right. So for the kinetic energy, we have that the value for the kinetic energy is 3.152 times 10 to the minus 3 joules. So I'll put it back into this equation. And then the work function, we have that. So let me write it out here. Kinetic, the work function was given to us as 2.158 times 10 to the minus 35 joules. And then the kinetic energy from the other slide, we found 3.152 times 10 to the minus 3. 3.152 times 10 to the minus 3. So, and of course, you know your Planck's constant H is simply 6.6 times 10 to the minus 34 joule second. So this is in joule, this is in joule second. So clearly, if I put those values into the formula, I have that the F, which is the frequency, becomes the work function 2.158 times 10 to the minus 35, adding up with 3.152 times 10 to the minus 3. Everything there divided by the Planck's constant, 6.6 times 10 to the minus 34. So somebody should simplify that and tell us what the answer would be. Firstly, add up the numerator, and then you divide it by the denominator. That gives us a value for the frequency of the photon. Please, what would you get when you divide this? Okay.
3.27
Yeah, I'm listening.
3.27 times 10 to the power of 33.
3.27 times 10 to the power of 33. Okay. Now, I don't know how true that is, but the point I'm trying to say is that anytime you have equation, look at the only thing I want you to get out of this whole thing here. Understand, always record this equation, because I think I brought in wrong values, because that value you got there shouldn't be what the value should be. All right. So I think the values are wrong from the equation itself. The solution is not wrong. I don't know whether the value, whether what she gave from her own calculator, whether it's correct. But what I'm saying is that the value given in the equation, I made a mistake with one of the values, and it affected every other thing we are doing right now. But from what we did, the solution is accurately done, because you saw how I made the subject formula by making first the substitution of my E, which is equal to HF. I replaced the E with the HF, and then I made the F subject, and then I saw what I did right here. So if you plug in the value for the work function and the kinetic energy and divide by the Planck's constant, anything you get out of that point should give you the frequency of that photon. And that's exactly what you're supposed to do, but with the right value. So, but I'm thinking that I put in the wrong values in the question, which is the reason why that solution is looking somehow. Or it might mean that the value you guys are calling out from your calculator is wrong. So either of that, because I don't have a calculator right here to verify. But let's go back to the question I said we're going to solve, that of the cutoff frequency. So please try to do this on your own, and be sure, do it on your own and get your own result. Every one of you should have a calculator. Whatever thing you get, that is your threshold, that is the frequency of that photon as required by the question. Now let's go back to that one that asks us to find the work. What are we looking for right here? The work function of a tungsten is 4.52 electron volt. Find the cutoff potential for photoelectrons when a tungsten surface is illuminated with radiation of wavelength 2.50 times 10 raised to the power 7 times 10 raised to the power 7 meters. Okay, so how do we solve this problem? Still the same equation, right? E is equal to the work function adding up with the kinetic energy. And now the question says we should find the cutoff potential. The cutoff potential, look at it. We need to find the kinetic energy first. If I find the kinetic energy, I can now find my cutoff potential. All right. So I need to find what the kinetic energy is. And once I find the kinetic energy, whatever thing I have, I can now use it to find the cutoff potential, because I can equate the kinetic energy, Ke, is equal to the charge of the electron multiplied by the cutoff potential. So the cutoff potential, V sub C, is equal to the what? Kinetic energy divided by the electron charge, which is constant 1.602 times 10 raised to the power minus 19 coulombs. All right. So the first thing we need to find is the kinetic energy. And once we find the kinetic energy, you divide the kinetic energy by the charge of the electron. That gives us the cutoff potential in volts. Okay. So let's find the kinetic energy first before we do the whole of that. So how do we find the kinetic energy? If you make the kinetic energy subject from this equation, of course, we have that the kinetic energy is simply given by as what? The energy of the photon minus the work function. So the energy of the photon minus the work function is going to give us the kinetic energy of that very electron. All right, which is the energy with which the electron is being emitted or ejected. But how I was given the work function, I wasn't given the energy of the photon. So how do I find the energy of the photon? From the question, I was given the wavelength. All right. Remember that H, that E is equal to what? HF. But I wasn't given what? F, was I? No. But I know that F can be written in terms of what? the speed of light, c, and of course, the wavelength. Remember, I told us that c is equal to what? F lambda. And if c is F lambda, F becomes c all over what? Lambda. Of course, so if I make that substitution right there, which I did before, this equation can also be what? Written in terms of hc all over lambda. So it means that I'm going to put c. C is a constant. And what is c? C is simply what? Speed of light. And c has a value 3 times 10 raised to power what? 8 meters per second. That's the value of c. So 3 times 10 raised to power 8 meters per second is the value of c, and is a constant every one of you right here should know. So you simply multiply the c by the Planck's constant and divide it by the wavelength. That would give us the energy of the photon, all right? And once we've gotten the energy of that photon, we can now subtract the work function from the energy and get the kinetic energy of the electron. So let's do that. Let's do that. Let me take this a little bit upward. All right, let me write out the parameters here. Solution, I'll write out the parameters again. So we were given that the kinetic energy, no, we were given the work function from the question. The work function was given to us as 1.33 times 10 to the minus 16 electron volts, right? No. The work function was given to us as 4.52 electron volts. 4.52 electron volts. I'm sorry for the continuous moving of my screen. So 4.52 electron volts. That's the first thing given to us there. And also we're given we're asked to find the cutoff potential, and then we were given the wavelength as 2.50 times 10 to the 7 from what I wrote down before. 2.50 times 10 to the 7, and of course the Planck's constant. Those are the things we are given. So the wavelengths 2.50 times 10 to the 7. We are looking for the cutoff potential, which is, we're given the Planck's constant H should be 6 points. Where's the value again? Where's the page? 6.6 times 10 to the minus 34. 6.6 times 10 to the minus 34. So these are the things given to us. And if I convert the work function to electron volts, I'll be having that this work function is equal to 4.52 times 1.602, which is 1.6 times 10 to the minus 19. So someone should help me get the value of this in electron volt. So when I multiply 4.52 times 10 to the times 1.6 times 10 to the minus 19, what would the value be in joules, please? While I wait for you to do that, remember we are looking for the kinetic energy. We said, recall that the energy of the photon is equal to the work function plus the kinetic energy. It therefore means that the kinetic energy is given by the E minus the work function. And what is the E? Wasn't given, but then we can find E. E is HF, which is equals to HC all over lambda. Where C is the speed of light, which is 3 times 10 to the 8 meters per second. So we can find our E. The E becomes 6.6 times 10 to the minus 34, multiplying the speed of light 3 times 10 to the 8. Everything there divided by the wavelengths, which is actually 2.5 times 10 to the 7. 2.5 times 10 raised to the power 7. So before we go back to, someone should tell me what the value of this would be. So multiply this and tell me. Before we get the work function in joules, let's get our energy first. (6.6 times 10 to the minus 34 times 3 times 10 raised to the power 8, everything divided by 2.5 times 10 raised to the power 7. So what would that give us?
7.92 times 10 to the power of minus 33.
7.92 times 10 raised to the power minus 33. That's the energy in joules. So also check for me the work function. When we converted the work function to joules, what did this give us? This value right here.
7.232 times 10 to the power of minus 19.
So the work function in joules is 7.232 times 10 raised to the power minus 19 joules. So I've both gotten the values in joules. So the next thing I would do would then be to subtract kinetic energy becomes the energy minus the work function. So it means that therefore our kinetic energy, Ke, is simply the energy, which is 7.79 times 10 to the minus 33 minus the work function, which is said is 7.232 times 10 to the power of minus 19. So 7.232 times 10 to the power of minus 19. So when you subtract these two things, what would that give us?
Minus 1 times 10 to the power of 33.
Minus. Oh my goodness. No. Please, go back to this problem. Look at this. Check this thing again for me. But at this time, put the 7, let it be 14. Change this power to 14. Let me confirm something. Do this again and change the power there to be 14. But there's no way I'm going to get a negative sign. I lifted the question from a past question, but I think there's problem with those questions. Okay, yeah. What did you get when you change it to 14?
7.92 times 10 to the power of minus 40.
No way. Just no way. Okay, just like I said, I lifted the equation from a past question, but I think those values there are wrong. The calculation, what we are doing is not wrong, but the values we are having is actually, we are getting is wrong. And that's as a result of wrong values given in the question. So I will just stick to what you got, okay? But have it in mind that I don't think that kinetic energy should be negative, but we're already getting a negative value, all right? So the energy shouldn't be a negative value. But due to the fact that the values given in that question are not all correct. It's either due to omission from my own end, or maybe the questions were just all wrong. And I can just go back to start checking out those questions again. But just take note of the process, how I'm doing what I'm doing right here, so that by the time I send, because I'll upload an assignment on the platform for you to check, and I will ensure the values given in those assignments will be very accurate. Okay. So I just lifted these ones from past questions, and it's obvious the values there's a typo error, which is making our values look incorrect. So what did you get as a kinetic energy again? Let's write it out. Let's work with that for the sake of this class. So when you subtracted this, what did you get again? What did you get, please?
I've deleted it, but it says minus 1.2 times 10 to the power of 33.
Okay. All right. Have it in mind that this value is not correct, but we are working with it just for us to finish up the solution we are dealing with. All right. Every solution right here is correct. Just the values are the problem. The values given in these questions are not correct at all. They are not correct at all. But the solution is very, very, very correct. So having found the kinetic energy, we can now know but KE cannot make your equation to find the cutoff potential, but KE is equals to EVC. So it therefore means that it implies that our cutoff potential VC is equals to KE divided by the E, where E is the charge of the electron. So clearly I'll be having minus 1.2 times 10 to the 33, everything there divided by 1.6 times 10 to the power of minus 19. So assuming this value for the kinetic energy is correct, the ratio, once we divide this value, that kinetic energy by the charge of the electron, that gives us the what? The cutoff potential. That's the cutoff potential. That is the potential that is needed for that ejection to occur. So if the cutoff potential, remember kinetic energy is the energy with which the electron moves. All right. So for the electron to be set in motion, for them to be ejected, there needs to be a cutoff potential. And that cutoff potential is what we are asked to find. And due to the fact that we are giving wrong values, or I gave wrong values in this question, everything is looking almost incorrect. But take note of the solution, which is very, very important. So let's just proceed with few more things. With few more things. Few theoretical things that you still need to know under photoelectric effect, and that is X-ray. I just want us to know X-ray, the uses of X-ray, the disadvantages, and just stuff like that. So that is what I want us to know right here. Because if you're a student of past question, or you've been going through some past question, you would have seen questions where you're being asked things like list 3 importance of X-ray, stuff like that. What are the effects of X-ray and other things? So X-ray was actually discovered by Roentgen in 1895. So Roentgen discovered X-rays in 1895, and they can pass through most substances, including soft tissues of the body, but not through bones and most metals. Of course, you know that X-rays are being used in the hospitals. Many a times, you should have heard maybe people have fractures or something happened to them, they go to the hospital and they want to check what is wrong with them. So what they do is that those people are being x-rayed. So the x-ray passes through your body and then it gives us the what? The bone imagery of that person. Do you understand? So it can actually penetrate your body, but it can't penetrate your bone. So we can know what is actually happening inside your body using an x-ray. All right. So the thing is that basically what I want us to know on this, because you might not be asked to define X-ray, neither will you be asked to who founded X-ray. All this information given here is basically for information's sake, for us to have it at the back of our mind, so that at any point we are going through the questions, we are reading through the topic, we just have a good background. That's all. The things you will expect to see under this topic, you can do well and read up these other ones for yourself. The notes are there. I just put down some few things for knowledge sake. So you can do well and just try to study them, read them out for yourself and have them in your mind also. But I want us to go straight into the properties of X-ray. Of course, you know that X-ray is an EM wave. It's an electromagnetic wave. So they travel in straight lines. They undergo reflection and diffraction. They are not affected by electric and magnetic field since they are not charged particles. The ionized gases causing them to conduct electricity, they affect photographic films. So I put down 5 properties of X-ray, and I want us to take note of those 5 properties even as we proceed with our preparation for the exams. Another thing you should take note of, having known the properties of X-ray, I repeat again, they travel in straight line, they undergo reflection and diffraction. Of course, they are rays, they are wave. And one part of the properties of wave and rays is that of course they undergo reflection. Every wave reflects, all right? Of course, waves diffract. So X-ray undergo reflection and diffraction. They are not affected by electric or magnetic field because they are not charged particles. All right. So if they were to be positive or negatively charged, they would have had an effect in either of these fields. They also ionize gases, causing them to conduct electricity, and they affect photographic films. Now, the next thing is that dangers of X-ray. Of course, you know that these things, when exposed to the body, it also has some dangers. And one of them is that it can destroy or damage living cells when overexposed. So when your body is being overexposed to these rays and radiation, it can actually cause a damage to your living cell. Excessive exposure of living cells can lead to genetic mutation. Of course, being damaged. The next thing is that okay, the third one is that as a precautionary measure, X-ray tubes are shielded by lead shield. And then the whole of those things, you can just do well to just check them out for yourself. And uses of X-ray, we have the uses in medicine, the uses in industry, in these uses in security. And under the medical use, we say that X-ray photos called radiographs are used in diagnostic to various diseases. Of course, you know that cancer, it can be treated using X-rays. All right. That's called in radiotherapy. Cancers can be treated using X-rays, and that is part of this application in medicine. Of course, you already know that your body can be scanned to know the state of your bone also using these X-rays. So we have industrial uses also. They are used to photograph and review hidden flaws. So in industry, let's say materials are being designed, and then some of the flaws of those materials, of course, you won't see them looking at them. So if you want to really find out the state of those materials in terms of what their flaws looks like, you can expose them to X-ray. Such radiation can tell us what the hidden flaws look like the casting and the joints. You will know where there are issues and the rest of that. So that is part of the industrial use of X-ray. And of course, in security, X-ray also has its application or its use. It's used in military and airport installation to detect dangerous metallic objects. So if you get to the airport, for instance, you find out that before those security measures, you have to be checked. And part of what they use in trying to ascertain whether you have anything dangerous, like a gun or any explosive gadget, is that they use this radiation. They expose you, even though you might not know, but you're being exposed to this radiation so that they ascertain whether you have something that can cause damage to anyone or even take life to anyone in that airport. So these are few uses of X-ray. Basically, what I want us to do is that I want you to go back and check, master these equations we've talked about in this class. Look at the very first equation. Let me go back to where we started. Firstly, we talked about photoelectric effects, and I defined photoelectric effects. The next thing we talked about the work function. On the next thing, which is what we have right here. And then we talked about the threshold frequency. I also talked about the factors affecting photoelectric effects. And then we also talked about the Planck's constant, the Einstein's photoelectric equation, which is what we have here, which is the general equation we use in solving problems involving X-ray and these questions like that. So this is the general equation involving the combination of the Max Planck's equation and that of Einstein gave us the general equation for the photoelectric effects. And then we also use them in solving problems. And I said, everything we've done so far in this problem, the solutions are all correct. The only problem is that the values given here are not right values. So you can see here, this wavelength was given us 2.50 times something. So there was an omission, and I didn't notice that at all. I just lifted the question from the past question, and that is why the value is giving us something negative, which shouldn't be, all right? So that is one. And also for this other question also, where we're asked to calculate the cutoff potential, right? Calculate the frequency of the photon. Okay, we did this and we arrive at the frequency. Where did we solve this one? One point 4.5 to 9.7. Cutoff potential. This was where we calculated the cutoff potential, and then okay, here this is it. Okay. Okay, I'm sorry the network logged me out, but I think I'll be ending the class right here. So please do well to go back to the video and check through the things you don't understand. You can do well to drop a question, or maybe in our next class, we throw more light on some of these questions we did that the values were actually not correct. Okay, so I thank you for your time. Thank you for joining the class. For many of you that stayed, you have two persons just, every other person has left, Obaomi and Christine. So maybe in our next class, we'll take more questions and I'll throw more light on this very thing. What did you say?
What's the topic of today?
Photoelectric effects. You came so late. That's why you're asking the topic. The topic is photoelectric effect. So I will upload the video, and in our next class, we'll also take further questions to. I know there are a whole lot of misunderstanding due to the questions, the values, and everything. The rest of that, I'll clear that off in the next class. So please, for now, we end the class. See you in the next class, and have a good night, right?
Thank you, sir.
All right, you're welcome.